to arrange, and so we are trying to improve our schedule. So let me introduce the first speaker of the session, Sergei Efimov, and let me also ask to all the speakers to stay on time. So I'll show 8 minutes and 2 minutes, okay? Something like that, in order to let at least 2 minutes for questions and shifting to the other, to the next speaker. So Sergei Efimov is introducing a work in collaboration with Vladislav Sidorenko about non-integrable model describing celestial bodies dynamics in first order in motion resonance.
Do I do this?
Yes, if you want.
Okay. Good afternoon. Hello. First, I would like to thank the organizing committee for this opportunity to speak out at this conference. And today I will basically present my work that I've done with my supervisor, Vladislav Sidorenko, on basically the analytical model of first order mid-motion resonance with chaos. So here is the outline of my presentation. So I'll speak about the problem itself and mathematical model that we used. Then I'll introduce some chaotic effects that are in the model and confirm some of the conclusions by presenting the results of numerical simulations based on data of real objects. So here's the problem. We consider the circular restricted three-body problem, which contains the star, planet, and some minor body, or the asteroid. Or because the first object of our interest was the Kuiper belt, I sometimes will refer to them as the Sun, Neptune, and Kuiper belt objects, because there are two big classes of objects in Kuiper belt with first order mid-motion resonances with Neptune, and they are of course Plutinos that are in 2 to 3 mid-motion resonances, and Tutino that are in 1 to 2 mid-motion resonance. And our goal was to construct an analytical model that includes the effects of second order of approximation in respect to eccentricities and inclinations. So the model that we used basically followed the general approach introduced by Jack Wisdom in the series of his work starting from 1985. And I wouldn't go much into detail here, but the original three-body problem is averaged along the orbital motion, then the disturbance function expanded into a series for eccentricities and inclinations. We truncate this series after the terms of second order, and after some non-dimensionalization and changing of variables, we obtain the Hamiltonian system with 2 degrees of freedom. And here is the Hamiltonian for this system. Function W is represented on the slide, and as you can see, the last term here is appears due to the fact that we use second order of approximation. If we use only the first order of approximation, this term vanishes, and the system becomes somewhat, it becomes the special case of the system that was considered by Sessin and Ferraz-Milot in 1984, and they showed that this system is completely integrable. What I want to show here is that introduction of the additional term destroys this integrability in the some region of phase space, and also produces a number of new qualitative effects. Here's some details about the Hamiltonian of the system. The formula for Hamiltonian is given above, as you can see, and on the right side there are equation of motion for Hamiltonian systems, and they have symplectic structure of special kinds. And For two equations, there is a small parameter due to previous non-dimensionalization of time. Thus, the characteristic speeds with which variables change in time differ significantly for the pairs of variables. So we can call first pair of variables fast variables, and there are resonant angle, which is the sum combination of orbital elements of asteroid, and also mean longitude of planet, and some conjugate momentum. Slow variables, the pair x and y, have a quite complex structure, but for small eccentricities, they can be viewed as eccentricity multiplied by cosinus of argument of perihelion and eccentricity multiplied by sinus of argument of perihelion. Thus, because we have two different time scales, we can first analyze only fast subsystems. Thus, we consider slow variables to be just parameters of the problem, so we fix their values and consider the dynamics of system described by this Hamiltonian in respect to variables phi small and capital Phi. As you can see here, this term can be interpreted as a kinetic energy of the system. Thus, function W is just the potential in which some point mass is moved. And due to the Hamiltonian, because Hamiltonian doesn't depend on time explicitly, its value remains constant. Thus, we can also denote it as some constant value xi and see how the behavior of the system changes with respect to this parameter. For different relations between potential and Hamiltonian level, we can obtain three qualitatively different behavior of fast subsystems. Thus, if Hamiltonian level intersects the potential in 2 points, we have the oscillation inside the potential well of resonance angle. If Hamiltonian level is lies above the potential, then the resonance angle circulates, and if they intersect in 4 points, and there aren't any other cases because the potential is just biharmonic function. Then for this case we have two different liberating solutions for fast subsystem. And here are some animations that should somewhat give an idea of what these motions are. Thus, because slow variables x and y are just the parameters of this problem, we can separate the phase space of x and y onto regions corresponding to different solutions of fast subsystem. And here are some examples of these regions for different levels of Hamiltonian. Here, first liberating regime corresponds to the white area, which lies in the most parts of the phase plane. Circulating regime corresponds to this green area in the center of the phase plane at large values of energy of Hamiltonian level, and two liberating regime exists in this orange area. Here are some also pieces of this area. The last black region corresponds to the case where the energy level lies completely below potential, thus the system can go there, so it's forbidden region. After we classified the motion of fast subsystem, we can obtain the solution for fast subsystem, and after that average along the solution of fast subsystem the equations for slow variables. So we change the right parts of Hamiltonian equations to their average value, and thus we obtain the system with two variables that is complete. Thus we can solve it and obtain phase portraits of slow variables. Here here there are four different levels of Hamiltonian. And one thing that should be noted here is that in the orange region, there are two different liberating solutions for fast subsystems. There are two families of trajectories on phase plane of slow variables. And here the complete classification of different trajectories that exist in the space of slow variables, and also how this properties changes over time is described by this bifurcation diagram. I wouldn't go much into details here because I'm a bit constrained by time, but the main thing that will be noted here is that in some region, for some values of energy, there are four different large families of trajectories on the phase plane. Thus, first trajectories rotate around the beginning of the reference frame. The second and third rotate around some positions on vertical axis, and the last one rotates around this whole portrait. And the purple line on the picture here is the separatrix that separates these four different types of trajectories from each other. That's all for the system, and now I'll describe some chaotic effects that are present in the system. There are two main mechanisms that leads to the rise of chaos in our problem. The first one we call adiabatic chaos, and it emerges due to the fact that adiabatic approach that we took doesn't apply to the system near the border between regions with different motions of fast variables. And the second one is geometric chaos, and it emerges due to the fact that in orange area, where we have two different liberating regimes, we have two families of trajectories. Thus, on the border between orange area and any other area, there are always meeting three different types of trajectories. And when two of these trajectories goes from the border, the fact which of the trajectories will took place is quasi-probabilistic event. Okay. So adiabatic chaos, as I said, rises because of the non-applicability of adiabatic approach near the border, and it leads to the quasi-random jump of trajectory when trajectory crosses the border. Thus, every trajectory that goes from one region to another, due to the series of such quasi-random jumps, will fill the whole area that we call stochastic region. And in this area, all trajectories are always mixed with each other. So the system always drifts from one part of the of this region to another. And for geometric chaos, we can calculate probabilities of different trajectories along which the system will go out of the border. The general formula is presented in works of Neistat, and here are some plots for the probabilities of three families of trajectories for different values of Hamiltonian. And finally, I want to conclude the presentation by showing some pictures of numeric simulations that are based on the simulation of whole solar system with 8 planets and about several hundreds of Kuiper belt objects. The data about Kuiper belt objects were taken from real observational data. And most of the objects lie outside of our region that we consider it, and they are interesting, but there are several of them that shows the behavior very close to the one that we expected them from our analytical model. Here's one example from the object 1999 CY13, and here you can see that its overall behavior is similar to what is expected on this trajectory of XY phase plane. But the other example that I like the most is the object that due to the diffusion in stochastic region, change its behavior and goes from rotating around the center of the phase plane along the trajectories of family that is denoted 1 here, to the rotation about some position on the vertical axis that is represented by trajectory 2, and after that it goes around this whole area by exiting this region and going along the trajectory 3 of the picture. And the other thing that we can look at is the behavior of resonant angle. Here is the plot for dependence of resonant angle on time for this object, and as it can be seen, different parts of this plot corresponds to different types of fast subsystem behavior. And the transitions between these different regimes corresponds to the trajectories of this type of trajectories on slope subsystem, where it also leads to constant switching between these two different behaviors of resonant angle. So to conclude, in our work, the analytical model that describes behavior of systems with first order motion resonance were introduced. Also, all scenarios of secular evolution were classified and introduced some chaotical effects that are present in the model. Some of them were quantified by calculating probabilities and other properties of emerging chaos. And all of the conclusions were corroborated by the series of numerical simulations that first validate the applicability of our model to the real objects, and also confirms the significance of the first or of the second order approximation, or the second order term that we introduced, because there are really some objects in Kuiper belt that live in this part of phase plane. Now, thank you for your attention, and if you have any questions, you can always direct them to me at this email, or if we have time now, you can ask me, and I would like to...
We actually have time for 2 minutes of questions or remarks.
I want to ask you if your model shows the same classification for all the resonances. For example, in the beginning, we talk about Plutinus and Plutinus.
Qualitatively, the Hamiltonian stays the same for all first order motion resonance. Coefficients between in front of the terms can be different, but the overall formula will stay the same for all first term resonances. Yes.
Because because the 1 to 2 resonance has also shows some asymmetric orbits, while the 2 to 3 no. But some models from other people, they show also that there are symmetric orbits in the 2 to 3 resonance. So we have the same classification, but this is not correct in the real proof.
Well, we didn't consider this effect yet, but I think we'll look at into it in the future.